Hello everyone and welcome to my channel. Today we are diving into how machine learning can help us predict satellite collision risk in low Earth orbit. With so much space debris out there, this is becoming a serious issue. I'll be showing you how we can use two supervised learning models that are random forest and support vector machines to analyze satellite data and figure out which object might be at risk. We'll talk through the whole process from cleaning the data to training the models and check how well they perform. So let's get started. Let's take a quick look at the dataset used for predicting satellite collision risk. I use a real world space object dataset containing object parameters and physical properties of satellites and debris. The training set include around 160,000 entries, while the test set has include around 20,000 entries. Each data points include features like distance between objects, relative velocity, size, kinetic energy, and more, essentially capturing the physics of potential collisions. I built a random forest model to predict satellite collision risk using a supervised learning approach. This algorithm constructs multiple distant trees by training on random subset of data and makes predictions based on majority voting across all the trees. This method improves both accuracy and stability while helping to reduce overfitting. I choose random forest because it performs well with large datasets, is versatile enough to handle both classification and regression problems, and is robust against missing values and noisy data. Let's look at how I train the model. To begin, first I import necessary libraries and started with processing the dataset. I dropped 11 columns such as ID and object descriptions that would not help with predictions. I cleaned any missing values and replaced infinite values with large constants to keep the data valid. Then I applied standard scaling to normalize the feature values so that model could perform better across attributes with different ranges. Next, I engineered a new binary target variable marking encounters as either low risk or high risk based on a collision risk threshold of -10. This threshold helped balance the classes and sharpen the model's ability to distinguish between them. After preparing the data, I split it into training and testing sets and trained the random forest classifier. I kept the model's hyperparameters fairly standard for a first run, and even without extensive tuning, the results were outstanding. The accuracy of the model on the test set was an impressive 98.7%. But accuracy doesn't alone tell the whole story. When I looked at the classification report, the precision, recall, and F1 score for both classes were incredibly high with near perfect values for both risky and safe classification. This means the model could reliably identify true positive and avoid false alarms. The confusion matrix further confirmed this, showing very few misclassified cases. The majority of predictions fell correctly into either high risk or low risk category, which is crucial for safety critical decisions. What truly stood out was the ROC AUC score. The model achieved score 1, a perfect separation between the two classes. That's as good as it gets, and it showed me that the model has learned the underlying patterns of collision risk extremely well. So, overall, the random forest model turned out to be a very powerful, reliable solution for this classification problem. It's not only gave me a strong predictive accuracy but also offered robustness and interpretability, things that are especially valuable in high stake domains like space collision predictions. Now let's take a look at my second model, that is support vector machine model I built to classify the risk of space debris collisions. SVM is a powerful supervised learning algorithm used for binary classification. In this project, I use the radial basis function or RBF kernel which help the model capture nonlinear patterns in data. Before training, I clean the dataset by replacing unknown values with none, removed irrelevant column like event ID and mission ID, and convert all data to numeric form. I handle missing values and infinite values by filling them with the median of each column. Then I created binary label classifying a risk higher than -10 as high risk and the rest as low risk. To ensure balanced learning, I made the dataset equal for both classes. Once the data was balanced and ready, I standardized the features using the standard scale. This step ensures that each feature contributes equally during the training phase, which is especially important for SVM as it's sensitive to scale of the data. With the data properly prepared, then I train the SVM model using the RBF kernel and enabled probability output so I could evaluate the model more deeply using ROC curves. Once trained, the SVM model achieved an accuracy of 82.79% on the test set. The classification report showed decent balance with both precision and recall score around 82% on average. The ROC AUC score was 0.93, showing the model a strong ability to distinguish between high and low risk events. The confusion metric also confirmed the model's reliability in identifying risky collisions. In summary, SVM model provide accurate balance predictions and demonstrated solid performance in classifying collision risk in space debris data. In summary, we explored how machine learning can help predict satellite collision risks using real world orbital data. We train and evaluate two powerful algorithms that are random forest and support vector machine with random forest showing higher accuracy and better overall performance. This kind of AI driven solution can play a key role in space safety and satellite management in future. Thank you for watching, and if you found this helpful, don't forget to like, share and subscribe.